Okay, so first of all, we'll just look back at the definition of it. The definition of it, you can see here, what the Laplace transform is here in definition 2.1. So we take a function little f, and this is normally thought of as depending on a variable t. And we do something to it. We do something to this function. We integrate it from 0 to infinity, dt, as you can see there, but it's multiplied by e to the minus st. So this introduces a new variable, s, into the transform. So that integral that we're looking at is actually a function of s. It's no longer a function of t, okay, because t is integrated out over the whole of its range from 0 through infinity. So the integral does not depend on t. It depends on the behavior of the function f and the behavior of that exponential factor. But there's that unstated variable s in there, and that's actually a complex variable. Okay. And this Laplace transform, its main use for us is going to be a device to solve certain types of differential equations. And it's made, like the logarithm example we talked about last time, it's going to proceed by taking your ODE, transforming the whole ODE into a completely different setting. So the ODE would feature, say, the function little f and its derivatives, it's the unknown function. Take the Laplace transform of the whole equation. It brings it into a new setting. But a simpler setting when you think of it for the purposes of solving it, solving for the unknown variable. And then you solve it in that alternative setting, and then do an inverse transform to bring the solution back to the solution to the original. But as I say, first we need to investigate it a bit more, find out how the Laplace transform behaves on some basic functions, and look at some basic properties. Okay? So the first example there, the simplest function we could take, apart from the zero function, the simplest function would be the constant function 1. So that's an example 2.2. Switch this on. So we look at example 2.2, and we'll also say a bit more about the nature of the complex variable s. Okay, so here the function is f defined by f of t equals 1 for all t greater than or equal to 0. Okay, so it's the constant function 1. So we want to take the Laplace transform of this function f of t. Alternatively, we could write that as the Laplace transform of 1. So remember, we're using a kind of script L, a kind of handwriting calligraphic L to denote the Laplace transform. That's traditionally what is used. Well, we just use the definition. So the definition says to integrate from 0 to infinity e to the minus st times the function that we're transforming. Now, we're transforming the constant function 1 here. So, I mean, I could write down multiply by 1, write down an extra factor of 1 there, but you know, by convention, we wouldn't bother putting that, writing down a factor of 1. So it just reduces to this integral. So this is an integral of the exponential e to the minus st dt, and then there's that unspecified parameter s in there. So because this is an integral over an infinite range, it raises the question, does this integral converge? Does this integral converge? And the answer to that question will probably depend on s. because you're integrating e to the minus st dt. So depending on the nature of s, for some values of s it might be a convergent integral, for some values of s it might diverge. Okay. Now s is actually taken to be a complex variable, so we could let s be a plus ib, where a and b are both real. So then, continuing the Laplace transform, then we can integrate e to the minus st. Integrating e to the minus st without looking at its real and imaginary parts for them. It's going to be e to the minus st over minus s. Okay, so you're integrating with respect to t, remember? And then you have the limits t equals 0, t equals infinity. And this will evaluate to the limit as t goes to infinity of e to the minus st over minus s. That's what you get when you evaluate the integrated function at the upper limit at t equals infinity. Really, you're taking the limit of it, t approaches infinity. And then minus the evaluation at 0. Now, the evaluation at 0 is pretty straightforward because when t is 0, we're just looking at e to the 0. E to the 0, of course, is 1. So this will be minus 1 over minus s, so in other words, plus 1 over s. Okay, so that's what it's looking like, but it may or may not be a valid value, depending on whether or not this limit exists. If this limit exists and has a certain value, then the result of the transform will be whatever this value is plus 1 over s. But if this is divergent, then this expression doesn't have a valid value. Okay? You're adding 1 over s to something that isn't defined. Okay? So the whole transform won't be defined for perhaps for certain values of s. Now we'll park this for the moment. Park this for the moment and just consider the limit as t goes to infinity of e to the minus st. Consider just how that part behaves. Well, this is going to be the limit, and now I bring in the real and imaginary parts of s. E to the minus a plus ib t. If it does real and imaginary, that exponential now, it's an exponential to a certain power, but the certain power is a sum. Minus at plus minus at minus ib t. So we can split up the exponential into the product of those two exponentials. This is going to be e to the minus as multiplied by e to the minus ibt. Sorry, e to the minus 18. Now this is good to split it up like this because these two factors have quite different behaviors as t goes to infinity. You look at the second factor, e to the minus ibt. That's an exponential, e to the power of I times something. Well, those kind of exponentials, we know, live on the unit circle in the complex plane. Okay, so if this is the complex plane with its real and imaginary axis, e to the minus ibt, for whatever value of t, will just live somewhere. Will live somewhere on the unit circle. Okay, because it's an example of e to the I theta. E to the I theta lives the angle theta on the unit circle. And as t increases, all this does is just go round and round round and round the unit circle. Okay, so as in the limit, as t goes to infinity, this factor isn't converging. This is just going round and round and round the unit circle. Okay? Every time t goes through a range 2 pi over b, it will make one complete orbit around the unit circle. So this is as t goes to infinity. That's what's happening to e to the minus I t. But the other factor, the limit as t goes to infinity of e to the minus at, now that does do something. This limit is going to be equal to, well, you see, if a is a positive number, then that limit is going to be equal to 0. So if a is positive, then e to the minus at will be e to a negative number, and the negative number will be getting larger and larger in absolute value as t goes to infinity. So it will be like 1 over an exponential, it's getting very, very large, so the whole fraction will get very, very small. So it's going to have a limit 0 when a is strictly greater than 0. It will have, well, if a is equal to 0, it's kind of like a special case, this limit is always going to be equal to, well, the limit is going to be equal to 1. But it's going to be divergent for negative a. Or the limit is going to be plus infinity, really, for negative a, because when a is negative, then e to the minus at, remember t is positive, t is going to infinity, e to the minus at will be e to some positive number, and that positive number, a times t, will be getting larger and larger and larger. So that won't be convergent. And it's going to be equal to 1, the special case that a is equal to 0. So if you've got something if you've got one factor spiraling round and round and round the unit circle, and the other factor sometimes converging to 0, sometimes it's stuck at a constant value 1, and sometimes diverging, how is the whole thing going to behave? Well, you see, when you multiply these two together, if the first factor, if you're in the case a greater than 0, the first factor is converging to 0. So that will make the product spiral in and be convergent to the value 0 in the complex plane. Okay? Because this factor is going round and round the unit circle. The first factor is shrinking down to 0. So that will make the product, the whole product, e to the minus st, spiral in and converge to 0 in the complex plane. Whereas if the first factor is divergent, it's getting larger and larger, the whole product will spiral out. Keep spiraling over ever greater radii in the complex plane, so it won't be convergent. And the special case when the first factor is stuck at the constant value 1, well then the product is just going to keep spiraling around the unit circle. Again, that won't be convergent. It's not convergent in the complex plane. So the limit as t goes to infinity of e to the minus st is only convergent. It's only convergent when a, which remember this is the real part of the complex variable s, is strictly positive. And in this case, the limit is equal to 0. Okay, in the other cases, when the first factor is stuck at 1 or expanding, the behavior of complex number is going to be either spiraling around the unit circle or spiraling around the expanding circle, so it won't be convergent. So, conclusion is about the Laplace transform of the constant function 1. This is equal to 1 over s with the added condition that this is only defined for the real part of s greater than 0. Okay? That's the only case where the integral is convergent. So we take it that this constant function 1 has a Laplace transform. The Laplace transform is complex valued. It's a function defined in the complex numbers, and it's only defined for complex numbers in the right-hand half of the complex number. Complex numbers with real parts strictly bigger than 0. Now, do I make this remark in the notes? Yeah, so I haven't really made this point in the notes, so I'll make it now. Attached to all Laplace transforms are convergence conditions like this. Okay, so the convergence condition here was that the real part of s had to be strictly positive. So all the Laplace transforms that we use, they all have with them these convergence conditions. We won't focus on these, except for some examples at the start, because for us, it's just the existence of transforms which is important for our solution method for the ODEs, which is needed for the solution of the ODEs. So we will skip over the question of whether or not the thing converges, as long as we can see, that it will be convergent for some values of s. Okay, so there's another example there, example 2, which deals with maybe the next function in the list of standard functions, which would be the function defined by f of t equals t. So here we're considering f defined by f of t equals t for all t greater than equal to 0. So we could ask what the Laplace transform of this function is. I mean, this is more or less all done in the notes. So we're taking the Laplace transform of f of t. We could also write that as the Laplace transform of t simply. Well, according to the definition, this is the integral from 0 to infinity, e to the minus st times t dt. So there you're integrating a product of an exponential and the quantity t. Generally, integrating products of functions of t should be handled by integration by parts is one method you can do. Indeed, that's applicable here. So presented at the start, we'd like to present the exponential part as a derivative. So there I've just rewritten the exponential as a derivative of something, so it's a derivative of itself with this you scaling by minus s there. When you carry out that differentiation, you get back to e to the minus st. So we can then use integration by parts to say that this is the product of these two functions, t times e to the minus st over minus s, evaluated at t equals 0, t equals infinity. It's good sometimes to name the variable that the limits go in for when there's more than one variable in the expression, just so you don't get confused and start putting in 0 for s and so on. Okay, s is a free variable here. So that's the first part of integration by parts, and then we subtract the integral of e to the minus st over minus s times the derivative of the other factor, but the derivative of t with respect to t is of course 1. So I have an extra factor 1 there, which I multiply down, which is dt. So that was integration by parts. So we've got some stuff to consider here. So you have to think about how this behaves here when you evaluate it at the limits, t equals 0 and t equals infinity. Well, when you put t equals 0 in there, you see there's a factor of t at the front, so that's going to be 0. And when you put t equals infinity, well, what do we mean by that? Really, we mean taking the limit of it as t goes to infinity. And again, this limit will exist for certain values of s. Again, when s has a real part bigger than 0, then that exponential e to the minus st at the top, that's going to be converging to 0. Quite fast, exponentially fast. Okay, which is much faster than the t is increasing. So the factor t, even though this factor here is getting larger and larger and is unbounded, but for appropriate values of s with real part bigger than 0, that exponential part up there will be converted to 0 very fast. So that will drag the whole product in. So really, you'll just get 0 until 0 in the limit as t goes to infinity, and 0 at the evaluation t equals 0. Or let's just say for certain s. Those with real value, real part greater than 0. And then how does this integral here behave? Well, the minus s can come out, and we've got plus 1 over s, the integral 0 to infinity, e to the minus st dt. But this integral we have just done. This was the integral that arose here when we took the Laplace transform of the constant function. Okay, so we already know that that is equal to 1 over s for certain values of s, when s is real part greater than 0. So in total, it comes out as 1 over s squared. The integral 0 to infinity e to the minus st dt is equal to 1 over s, as seen before, seen above. So the whole thing comes out as 1 over s squared. So the Laplace transform of the function t then is 1 over s squared. So you get a new function in a new variable. These can be used for various things, but as we say, the main use we're going to put it to is as a way of solving certain differential equations. Because when you transform the differential equation, it will just turn into an algebraic equation featuring loads of different functions of s. Well, that's kind of a simpler class of algebraic differential equation. The algebraic equation we could just solve using algebraic manipulation, solve it for s, and then take an inverse transform to get back the solution to the original problem, to the original ODE. Okay, there's one more example there to do, which is the exponential function, but you've got it there in the notes on page 41. I don't think I have much more to add to it by doing it on pen and paper, so I won't. But let's just have a look at it. So there you're taking the Laplace transform of e to the minus at. Okay, so here, the Laplace transform of e to the minus at. you just apply the definition. So you're integrating the exponential e to the minus st multiplied by the function you're taking the transform of, which is e to the minus at. They collapse together, though, into one exponential, e to the minus s plus a times t dt. And again, that integral is one we've already done. We've just done it in the Laplace transform of the constant function. So the integral of e to the minus some complex variable times t dt is going to be 1 over the complex variable, 1 over s plus a. Again, there'll be a convergence condition there. The real part of s plus a would have to be bigger than 0. So the real part of s would have to be bigger than the real part of minus a. Is that right? The real part of a. So the real part of s would just have to be bigger than minus the real part of a. Yeah. Okay, so turning over the page then, you will notice, so this is an extract from the formula handbook that we use, that's available to you in examinations. There's a couple of pages there on the Laplace transform. So the first 2 lines we've proved, the Laplace transform of 1 and the Laplace transform of t, 1 over s and 1 over s squared respectively. And then down the left you can see a whole other bunch of functions, kind of standard functions, functions that typically might arise in the differential equations that we look at. Okay? And on the right-hand side are their Laplace transforms. So we may come back to some of these. We may come back to some of these as exercises and try deriving these Laplace transforms as exercises as we go through the unit. But we won't set ourselves that task now of doing all of those. Now we'll kind of do a few of them as we go through. Then over on the following page are also listed some properties of the Laplace transform and some results and some other strange looking functions, perhaps this unit step function h and the unit impulse function delta. Those are the Heaviside and Dirac delta functions, which we'll meet in due course. So those properties and the way the transform behaves, those are things we need to derive, we need to understand and prove. Now I did one really quickly at the end of the lecture last time. We settled theorem 2.1. Look on page 44, theorem 2.1, which is the linearity of the transform. So the linearity of the transform we state by saying that the Laplace transform of alpha f plus e to g is a general linear combination of 2 functions. This is alpha times the Laplace transform of f plus beta times the Laplace transform of g. So this is for functions f and g with transforms. So ones for whom the Laplace transform exists, and alpha, beta are real constants, or indeed you could allow them to be complex constants. We'll, in the applications we look at, though, we'll just be concerned mainly with real value functions. So this is a very nice property to have. Okay, when things are linear, they are more easily understood than when they're not. They have a very nice behavior, very nice expected conservative behavior on linear combinations. And you can imagine the concept from linear algebra being applicable to things like this. You know, when you have some major operation and when it's linear, that can bring in the theory of linear algebra as well. Okay, so is this a huge proof that we need to do for this? Is it a very deep result? Well, you might consider it that, but it doesn't require a lot of extra work from things we already, from properties we already use all the time. Okay? So this simply follows, and I don't like using the word simple too much, but because this simply follows from the linearity of integration. Now, whether or not the fact that integration is linear we regard as a simple part, be very careful to prove that using some first principles definition of integration. The integration is the Riemann sum, the limit of Riemann sums of a function. But the linearity of integration we use all the time. An integral of a linear combination is the linear combination of the integral. You use that all the time in the split up integrals. Take constant factors outside integrals. And really, since the Laplace transform is just defined as a certain integral, that property of integration just passes through to the Laplace transform. You just need to observe it. Well, it just kind of falls out once you put in the definition of what this Laplace transform is. So if the integral of e to the minus st times alpha f plus beta g, I suppose I should say t here for f and g. So there's an integral of, well, after you multiply in the exponential, you'll be seeing a linear combination, alpha exponential f plus beta exponential g. So you just split up the integral accordingly. So this is going to be alpha times the integral from 0 to infinity, e to the minus st f of t, plus beta times the integral 0 to infinity, e to the minus st g of t. But then what are you looking at in those two integrals? You're looking at exactly the definition of the Laplace transform of f in the first one and g in the second one. So when I say simply follows, I mean you just apply the definition of the Laplace transform, you see an integral of a linear combination, split it up accordingly, and then what we're looking at, you apply the definition of the Laplace transform again, and you get what you want to define. So this is a very nice property to have. If we want to take the Laplace transform of a complicated function, which is complicated because it's a linear combination of other functions, we can just find the Laplace transforms of the individual functions to get the transform of the whole. So let's look at the example 2.3, which follows this. So this is to take the Laplace transform of 3t plus 4e to the minus 2t. Okay, now this could be a problem like the other ones we've done earlier today, where we form the integral 0 to infinity of the exponential multiplied by this function we're considering, 3t plus 4e to the minus 2t. We examine the integral and evaluate the integral. However, we notice that the functions involved, well, we've already proved what the Laplace transforms are of the individual functions involved. And what we're looking at is just a linear combination of those. And we'd use the same approach if the functions we were seeing in here, the individual functions in there, could all be found on the table of Laplace transforms on the previous pages. So using linearity, we can say this is 3 times the Laplace transform of t, plus 4 times the Laplace transform of e to the minus 2t. Okay, and then make use of previous results. So this is using linearity. And so the Laplace transform of t was 1 over s squared, so we get 3 over s squared. And the Laplace transform of e to the minus 2t was 1 over s plus 2. Okay, so you could say from previous results or taking transforms from the table. Okay, any questions on that? Or? Okay, let's just deal with one more property here in 2.2. Should we? I think I might not, because I think we've covered enough to bring in the first set of exercises, and we're making good progress with the course, so I don't want to squeeze too much into the end of this. So if we just look at exercises 2.1, page 47, some good things here for you to be working on for the tutorials. The first one is just a little exercise, a very simple ODE. I mean, this ODE does not require any kind of advanced techniques. It's a third order ODE, but it only consists of a third derivative. So simply by integrating both sides of this a few times, you can get back to the function y there and obtain a solution. But this is an exercise in applying boundary conditions or certain conditions on the unknown function to determine the values of the unknown constants that arise from integrating both sides. We then got some exercises on Laplace transforms, and these are a mixture of taking, none of them are taking Laplace transforms in first principles. So the first one is using this expression for the hyperbolic sine function as a difference of exponentials. Using this fact and what we already know about the transforms of exponentials to then derive the transform of the hyperbolic cosine function. And you need to use linearity here as well. So you say, taking the Laplace transform of the hyperbolic sine, that's going to be the same as taking the Laplace transform of a half times the difference of those exponentials. And so you use linearity then to split it up, and then use the transform of exponentials and so on. Question 3 actually is a first principles one, be an exercise in integration by parts. So working directly off the definition, prove that the Laplace transform of t squared is 2 over s cubed. And then question 4 and 5 are exercises in working with the table and the property of linearity, I guess. Question 4. So just finding the transforms of these functions by working with the table and that linearity property. And then question 5 is finding some inverse Laplace transforms. I haven't taken the time to separately define what we mean by the inverse Laplace transform, but for the moment, you can just simply consider it as the reverse operation that's represented by the table. So you have a function of t here, and you take its transform, brings you to the right. But if you can find a function of s here, take an inverse transform, it brings you back to the corresponding function of t on the left. And you can also make use of the linearity property applied to the Laplace transform. Okay? If a function is linear and its inverse exists, then its inverse will be linear as well. So because the transform is linear, an inverse transform, which associates functions of t to functions of s, that's going to be a linear transform. So all those exercises there in exercises 2.1 should be open to you, so you can be working away on those. And we'll continue when I see you again next term. I'm not seeing you for electric and industrial. In this, we'll pick up and continue investigating the Laplace transform and work towards applying it to solve certain types of differential equations. Okay? Okay, so we'll end there for this morning.